Okay, so this is for the quiz for Dsp. This is signal processing. So first of all, the first question gave us the equation, which is x of t is equal to 20 to the exponent of negative 0.1 t of u of t. So we have a time domain signal. And then for question A, with a sample frequency of 10 hertz, so we have a sample period of 1/10. So for question A, it says that we have to find the DTFT, which is a discrete time Fourier transform. So the way we do it is we do the sampling first. This is the equation for sampling. So we define the sampling. So we got this is our sampling equation. And after that, we by using the DTFT definition of this equation and this DTFT properties and pairs, which is u of n DTFT, when we DTFT transform it, we have this equation. And also for when we have a terms of a of n times with a signal, when we transform it using DTFT pairs or properties, we also get the signals when a is less than 1. So for this equation, when we try to do the DTFT transform, so we got this equation as our DTFT of the sample signal. So this is the one. So the question B is that it tells us to find the sample signal of the xn, where xn is 0, 1, where the sample signal is at n0 up until 3, and we need to find the value for it for the sample signal x of n, which is the one that we get, which is this one, until n is equals to 3, up until 2 decimal places. So we do the same thing, and then we got the same signal, which is the same as this one. So when we do the sample signal of n is equals to 0, we got 20, x is equals to 1, 19.8, x is equals to 2, 19.6, and x is equals to 3, we got 19.4. So that is our question B answers. So since we have a properties of sample of unit step signal, which is u of n, when u of n is bigger or is equals to 0, we have 1. Un is equals to 1. When is less than 0 and is less than 0, we got a 0. So by using these properties, we can calculate for x of n, x of 1, x of 2, x of 3 by using this sample signal. By using this sample signal. Okay, so the next one is the question part C of question 1. So the question is, if xk represent the 4-point DFT of xn, find the x3, which is we need to find the xn of DFT, and then say that what is the assumption made to the xn when DFT is performed. So first of all, we need to do the DFT, so we need to find the sample signal, which is the one that I already got from the question 1a, and then by using the DFT definition of x of k, so by using this, and then we get this signal, this equation for x of k. And when k is equal to 3, we just plug it in straight away. So we do it up until 3, because x of k is this one, because we have this definition or assumption of k is equals to n minus 1, so we just plug it in, and then we start at n is equals to 0, x of n, our signal, and then some variations of exponentials. So when we do the calculation of x of 3, we have x naught, which is the one that we got from the previous question B. So we have x naught, x1, x2, and x3. So by using that, can calculate the approximate value of x of 3. So we do this calculations. So because we have complex exponentials, so we be using Euler's identity to simplify our equations to find the complex form, the complex equation. So this is what we got for x of 3. So the assumption is made is that the assumption is made is that the assumption angle is that when is n is equals to 4, when we're doing the 4-point DFT, it becomes periodic, and it's much more simpler than DTFT, where this one can represent a finite length of equations, whereas the DTFT, you have to do an infinite number to get the accurate measurements. So that is what we make for DFT. So for question 2, okay, so for the question 2, given the discrete time LTI, discrete time linear time invariant system as well LTI system equations, first of all, for the first question, it tells us we need to find the find the impulse response, which is h of n. So by simplifying the equation, we have the LTI system equation of y of n of x of n over 2 plus 1 over 8 y of n minus 1. So by using the convolution properties, which is this one, we can make an assumption that delta of n is equals to x of n. So by using that properties, we can put the delta of n over 2 plus 1 over 8 y n minus 1. So we need to have a couple of sample or couple of value for n, so we can measure is it accurate. So by letting the n 0, 1 to 3, we can calculate from y up until y0, y0 up until y3. So by using that, we can calculate everything up until y of 3. So because we have a unit impulse function definition, when delta of n, when n is equals to 0, delta of n is equals to 1 and 0 everywhere else. So we have these equations. We have y of 0 is equals to 1/2, y1 is equals to 1/16, y12 is equals to 1 over 28, and y to the third is y n is equals to 3 is we got 1 over 1024th. So by letting the y of 3 is equals to 1/2 times of c, and we can, because we have a common factors of 1/2, so we can make an assumption of 1/2 times c of n, some terms. So by using that, when n is equals to 3, we can do the calculation of c must be 1 over 8. So by using that equation or calculation we just made, we can say that by using the convolution sum properties of this one, we can make an assumption that y of n must be is equals to h of n. So that's why we have the h of n equation, which is equals to 1 over 8 to the power of n times 1/2. So for question 2b, it says that we need to find the system output for both frequency and time domains when an input x of n is equal to 2 over 3 to the power of m u of n. So by using that, since we already an equation of h of n and the convolution sum properties, so we can calculate the frequency for time domain system output, because we're already in the time domain system. So for that, we can just using the properties of this one of convolution sum properties, so we can just plug it in for x of n, for h of n, which is 1 over 8 over to the power of n, and then we just plug it in because we're using k, so we plug it in. Same with x to n minus k, so that we plug it in, so that n minus k, and then we just doing some algebraic, and then we have this final equation for time domain solution. So this is what we got for system output for time domain solution. So the next one is the we need to find the frequency domain for of that function of the system output. So the easiest way we can do is by using a z transform of the transfer function. So in order to get the transfer function, because transfer function already in the frequency domain, so by using that we need only just to z transform the h of n, x of n, and then by using the convolution sum we can just calculate it normally, and then by using z transform properties we can transform each equation that we have, which is h of n and the inputs, to get the y of z, the system output. So by using that we have x of z, which is this equation 1 over 1 minus 2 to the minus z of minus 1, because we follow these z transform properties or pairs. And then for y of z, for x of z, we got this equation, and then when we using the convolution sum properties, and then we got this for the frequency domain equation. So that is all.